Great. So welcome everyone. Thanks for joining this session. So today we will be giving a very special talk that is actually a joint talk between two groups of researchers on two papers published last year at NeurIPS. So both papers try to understand approximate inference in Bayesian neural networks, but they work on a slightly different angles. So to set out the context, so basically, if you join this session, then perhaps you know that the biggest problem in Bayesian inference is that you want to compute the posterior distribution and it is intractable. So we want to do approximate inference for that. So this also applies to Bayesian neural networks where you want to do a Bayesian treatment on the weight of the neural networks and then do posterior inference on it. So that means you also want to do approximate inference for the Bayesian neural network weights. So, in the literature, there is this, design for this Q distribution in simple forms and also in richer forms. For example, in the simple approximations, we have mean field Gaussian, MC dropout, etc. And we also have, attempts to try using richer approximations like low-rank Gaussian or normalizing flow-based approaches, etc. So basically, there are tons of research exists right now, but most of the result on right now is based on empirical evidences trying to evaluate the proposed algorithms on some data sets and see whether it works. So at least to me, the theoretical properties of these approximations results are actually less well understood compared to like the empirical evidence we have in the literature. So that's basically the background of the two research that tries to figure out the theoretical understanding of the approximation happen in Bayesian neural networks. And so that brings to today's lecture and discussions. So basically today we will first go through two short presentations. The first one by Andrew and David on the expressiveness of approximate inference in Bayesian neural networks. And the second one is by Sebastian and Louis on liberty or death. Deep Bayesian neural nets do not need to complex weight posterior approximations. And then after the presentation, then we'll go through a half an hour joint Q&A discussion with all the presenters and also the participants. So basically, I will ask you to save all of your questions or comments of any of the papers till this session. You can submit your questions via the Q&A function. And then when you submit the question, if you would like to actually, read out your questions or actually provide your comments, yourself, you can also indicate in the Q&A submission telling me that you want to actually speak out your question, then I will allow you to speak. So yeah, so without further ado, so then we will first go for the first presentation by Andrew. So I will let Andrew to share his screen.
Great, thanks very much, Yingzhen. Let me just share my screen. Cool, can I just check that everybody can see my screen, and like if I move my cursor around my screen, you guys can see that too?
Yes, I can see it.
Great, so I'll just start off then. So yeah, thanks everybody for coming for this talk. Today I'm going to present a paper called The Expressiveness of Approximate Inference in Bayesian Neural Nets. Like Yingzhen said, this is work that was done with David, with Yingzhen, and also with Rich Turner, who's my supervisor. So let me just get straight to it. What are the big challenges for Bayesian neural net practitioners and researchers? I'd say that they fall into two main categories. The first one being, how can we specify a good prior? So it's common to do very simple strategies like factorize Gaussian priors. However, there's been recent work on the cold posterior effect that suggests that actually there are challenges with this. Maybe our priors are not as good as we think they are. This has actually led to lots of renewed interest on discussing this problem, which I think has been a very interesting direction in Bayesian neural nets recently. The second major challenge for BNNs is once you've chosen your prior, how can we then perform good inference? It's an unfortunate fact that Markov chain Monte Carlo and variational inference, the two most common techniques, don't actually come with practical guarantees that that a practitioner can use to rigorously state that they're going to approximate the posterior well. And I think it's also an important question to figure out whether our performance is due to our Bayesian model or to our approximation. For example, if we're doing really well in our downstream task, but it's only because our approximation method is doing something peculiar, then maybe we shouldn't thank Bayes for our results. And conversely, if we're doing very terribly, Maybe Bayes itself is doing okay, but approximation is breaking things. And I think understanding why we're doing well helps us to decide, should we be more Bayesian in the future? Because if Bayesianness is good, then we should be increasing it. But if it didn't really have to do with being Bayesian, then maybe that's not the avenue to go for. I'd argue that these two challenges are actually linked. And one way to see this is that often we choose our priors by evaluating the posteriors that are induced by them. So here's a quotation from a Bayesian statistician who said, "Ye priors shall be known by their posteriors." What he's saying is that the way you evaluate a prior is you show it some data, you look at the posterior, and you think, is this a reasonable posterior? And I'd say that having a lack of reliable inference really hampers our ability to evaluate our priors or decide whether one prior is better than another. So with that in mind, this talk will focus on the second big challenge, analyzing approximate inference. To make sure we're all on the same page, we focus on variational methods, which assume some kind of tractable parametric form for the approximate posterior. So here I have on the left the predictive distribution that we want. Y and X star are new targets. Then it's the real solution is an integration against the true posterior in red, but we approximate it by integration against the approximate posterior in blue. Now, the blue posterior Q is chosen from a blue approximating variational family called curly Q. Most commonly, this is going to be the mean field of fully factorized Gaussian distribution, or it's going to be some kind of Monte Carlo dropout distribution. And as we know, we choose the member of the family that minimizes the KL divergence between the approximate and the true posterior. So you can imagine an initial distribution here, and then we do some kind of optimization. We end up with a final distribution, and it's close to the true distribution, but it can't match it exactly unless Q is sufficiently large. So let's take a step back and think about what criteria we need to satisfy for a method like this to succeed. I'd say, roughly speaking, first of all, the variational family must contain good approximations to the posterior. There has to be at least one member of the family that is good enough for you. And secondly, the method must then actually select a good approximate posterior within this family. It's not enough that these approximate posteriors exist. You actually have to choose them. Which leaves open the question, how can we tell if the approximation is good? What we really need is a reference. We need some way of saying that, okay, exact inference looks like this, or something close to this, and we know we're doing well because we look a bit like exact inference. Unfortunately, this is a very difficult problem in large models, I'd say, to get a reference for the exact posterior that we're actually very confident reflects the truth. We could do HMC, Hamiltonian Monte Carlo, but it is kind of slow, and it's actually hard to diagnose in practice. Like, there are hyperparameters you need to tune. You're never totally sure whether you've burned in long enough. One of the references we're going to use in this work is the idea that deep Bayesian neural nets approach GPs, Gaussian processes, as width increases. This is really nice because Gaussian processes, we can do exact inference in them. So you don't have to worry about MCMC or VI or anything like that. Here's a paper from Matthews et al. In 2018. In blue, we see the predictive distribution of a deep Bayesian neural net. And in green, we see the equivalent Gaussian process in the infinite width limit. Now, we don't expect the GP to exactly match finite Bayesian neural nets. And we don't expect Hamiltonian Monte Carlo to exactly match finite Bayesian neural nets either. But we hope that at least in small data sets for regression tasks in simple situations, we can get some confidence that we're obtaining a reference for the exact posterior that we can believe in and compare against. So with that in mind, how does mean field VI compare to this infinite width neural net Gaussian process? Let's consider a toy Bayesian optimization problem using a single hidden layer mean field VI network and the equivalent infinite width Gaussian process. So on the left, I show the GP. On the right, I show mean field VI. And I show a super simple optimization problem. I want to optimize the black curve, which just has a single maximum in the middle. Now, the red line is the mean of the GP prediction, or the mean field VI prediction. And the blue shaded region are the uncertainty regions. Now, we're going to use upper confidence bounds to do Bayesian optimization, which means we select the top of this blue shaded region. We select the sum of the mean and the uncertainty. And we can see that before we see any data, the prior looks kind of like a wedge shape, and the GP chooses a point on the left, and the mean field VI chooses the point on the right. They're both uncertain away from the origin. Now, after you condition on that point, the GP reduces its uncertainty, and mean field VI also does that somewhat. And then now they choose a point on the opposite end. And now something different happens. The GP is confident on either end, but unconfident in the middle. However, mean field VI is strangely more confident in the middle where it has no data than at the endpoints. Now, this means that at the next iteration, the GP picks a point in the middle, but mean field VI picks another point at the endpoint. And then when you condition on that, the GP after 4 iterations has basically solved the optimization problem, whereas mean field VI hasn't. It's still picking points at the end. In fact, we can continue this. Mean field VI keeps picking points at the end, 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 and again and again. And even after 15 iterations, all it's done is pick lots of points on the left and lots of points on the right. And that's because it was irrationally overconfident in the middle, even though if we did exact inference in a very similar model, it didn't have this kind of problem. So why is this happening? Can we explain this kind of behavior? It seems like something we should be concerned about if the prior in the model in exact inference does something good, but we lose it when we use approximate inference. So to help explain this, we prove a theorem in our paper. And just to clarify, in this section, f of x is going to be the output of the network, and v of f of x is the variance. So you can think of it as the uncertainty, and this is a regression network. So it's a predictive variance. Our first theorem states that there exist line segments in input space. We call them PQ, such that for any single hidden layer ReLU network, which uses a mean field Gaussian weight distribution, for all points R in this line segment, the variance at R is upper bounded by the sum of the variances at the endpoints of the line segment. What this is saying, and for example, one of the line segments we bounds includes line segments crossing the origin. So that would explain the previous case why I was always so confident in the origin. We prove a similar result for dropout networks, which shows that for any single hidden layer ReLU network with a Monte Carlo dropout weight distribution, if we don't apply dropout to the input layer, which is common practice, then the predictive variance is actually a convex function in X. And if you think of convex functions, they are kind of bowl-shaped. They can't have large regions of high variance in between regions of small variance, which is exactly what was needed to solve the previous task. So these theorems show that these particular one hidden layer Bayesian neural networks can't actually have any in-between uncertainty. And you can ask later for intuition for why this is the case. Now, we can numerically verify these theorems, and the way we're going to numerically verify them is that we first obtain a reference predictive variance function from a Gaussian process, and then we perform gradient descent to directly minimize the predictive variance, the square error between the predictive variance of the approximation and this target on the grid. So here, if you look at the top graph, what I have in blue is some target variance, and you can see that it's high in the middle and low at the ends, which is what you might want. And in orange, we have the fully factorized Gaussian predictive variance, and we actually directly try to make it match the blue target function. However, our theorem actually implies a bound, which is the red dotted line. And you can see that like we saturate the bound, but even when you saturate the bound, you don't really get the level of in-between uncertainty that the target is aiming for. The situation is even worse with MC dropout, because remember, the green function has to be convex. Convex functions can't well approximate this in-between uncertainty very well at all. And so it doesn't match the target, even if you directly try to make it do so. Now, that was an artificial approximation problem, but what about an actual inference task? So here, if we consider two separated classes of data in red, and on the top, we show two-dimensional input space. So it's a 2D regression task, and the colors represent uncertainty. So yellow is high uncertainty, blue is low uncertainty. And the dashed white line is a slice through 2D input space, which we then show at the bottom. Now, the infinite width limit GP and Hamiltonian Monte Carlo actually agree very closely here, which gives us confidence that both of these actually look a lot like the true posterior. And they both show a lot of in-between uncertainty, increased uncertainty between the clusters. But if we use mean field VI or MC dropout, we see that actually almost all the in-between uncertainty is gone, which is in accordance with the theorems that we proved. So in this case, approximate inference, rather than the model, is actually provably responsible for this bad behavior. So if we go back to the criteria that I talked about at the start, we have to say that if in-between uncertainty is something you care about, the first criterion that we must contain good approximations to the posterior in the family is simply not satisfied if you use mean field Gaussian or MC dropout for ReLU nets with one hidden layer. Hence, we cannot fix this by choosing a better prior, or by using a better optimizer, or by tempering our posterior, minimizing a different divergence, etc. It's actually a very strong restriction. But what about deeper networks? it turns out that we have a contrasting result. So deeper networks can, in theory, have in-between uncertainty. So this is what our theorem says. So let input space be any compact set, and let M be any target mean variance, any target mean function, and V be any target variance function. Then for any epsilon positive, there exists a sufficiently wide two-hidden layer ReLU network with a mean field Gaussian or MC dropout posterior, satisfying the condition that states that the expectation is close to the target mean and the predicted variance is close to the target variance. So it's like a universality theorem for the first two moments of the marginal of the predictive distribution for random networks. So if we go back to our criteria, if we think about deep networks now, it looks like if all you care about is the first two moments, the approximating family does contain good approximations to the posterior. So the open question is, will we then find these good approximations when we optimize the elbow? Well, if we look at our results, we show what we do is we consider 1 hidden layer, 5 hidden layer, and 9 hidden layer networks. So we're trying to consider the deep case now. And we define something called the overconfidence ratio, which is the ratio of the predictive uncertainty that the equivalent Gaussian process gives divided by that of the mean field VI solution. And if this is high, that means the GP is much less confident than the mean field solution, which might be taken as evidence that mean field is actually being overconfident. And we can see that even at the 9 hidden layer case, we're really an order of magnitude overconfident in between the clusters of data, which are the black crosses, and we're actually underconfident at the data. So it doesn't seem like depth is really helping with in-between uncertainty here. So let me just wrap up by explaining some limitations of our work and some conclusions to draw. The first obvious limitation is that references for exact inference is really difficult in large models. In shallow networks where we get HMC and the GP to agree, I'm pretty confident that we get a good job of representing the exact posterior. But in deeper networks, you might argue that even the GP might not be a very good reference, and it's mainly suggestive of what we expect the true posterior to behave like. Necessarily, we therefore focus on small-scale regression data sets where we can be more confident about our inference references. But of course, in real life, we're really interested with large-scale data sets and classification. The big limitation, I'd say, with our theoretical results is that our theorem about universality doesn't actually explain observed behavior in deep networks. So you can imagine that our first two theorems could explain why we lose in-between uncertainty. It's because the approximating family isn't large enough. But theorem 3 doesn't explain why, even when we go deeper, we still observe a complete lack of in-between uncertainty. It must be to do with the objective function, and we haven't really gotten a theoretical handle on that. Another limitation is that in-between uncertainty obviously isn't everything. It's something that's good to have, but it's not everything you care about in your posterior. But we'd argue that it's a good sanity check to try in your small models whether this simple desiderata is satisfied. And if it doesn't work in small models, maybe we're not so confident about large models either. And so just to reiterate our conclusions, approximate inference and mean field Gaussian and MC dropout posteriors can lose qualitative features of the exact predictive when you do inference. In 1 hidden layer BNNs, in-between uncertainty is provably absent because of theorems 1 and 2 that I mentioned. In deeper BNNs, in-between uncertainty is empirically lost, but we're not entirely sure why, because theorem 3 states that good approximate posteriors should exist in some sense, at least. And I'd argue we're still, as a field, very far from understanding the difference between exact and approximate inference in, for example, large convolutional networks that we're interested in practice. So thanks very much for listening, and I'll hand back to Yingzhen.
Great. So thanks, Andrew, for the presentation. So as I said, we will save the questions to the Q&A session. So then now we'll go straight to the second talk by Sebastian. So Sebastian, can you share your screen?
Yes, is that working?
Yeah, that works.
Great. Thanks very much, Andrew and Yingzhen. So we have a paper that's exploring a very similar set of questions from a slightly different perspective. And I think we get to an interestingly different place, and I'm looking forward to talking through that discussion soon. But before I do, I'll just give a little bit of a picture of what the main results that we have are. And the direction we're coming at this from is very much examining the trade-off between getting good posterior approximations to the parameters and a more general mindset about deep learning that like bigger is better, and you can often solve problems that are more interesting in a more powerful way if you just make your network bigger, add more parameters, and so on. And one thing that this leads us to is maybe a slightly different perspective on the question of whether if something fails in a small model, this should make us worried about large models. And instead, we're trying to look at when you do have large models, how might things start to work that did fail in small models? Because that might give us some understanding of what's going on with the approximations that we're looking at.
Hey, Sebastian, I think maybe the connection is a bit bad. So can you try switch? Yeah, Sebastian, you have some connection issues. I would suggest you to switch off your camera and see whether it helps.
Yeah. Okay. How is that? Any improvement?
I think it works. Okay.
Okay.
We maybe missed like a minute or two of the presentation, Seb. I don't know if you want to go back.
Oh dear. Okay. Well, so I don't know exactly what got missed, but the main point I was making on this slide is that like sometimes we might think that if it doesn't work in a small model, then it definitely won't work in a big model. But there are at least some times when neural networks surprise us, and things that do work well in large models don't work in small networks. And so there might be some value in both analyzing what happens in big networks and trying to understand how it might emerge that actually even using a very simple approximate posterior in large networks might give you a very powerful predictive posterior distribution, which for many tasks is the thing that we care about most. And so I like to start with what I see as like the grandfather statement of why we don't like the mean field, which comes from David Mackay's sort of first paper on Bayesian neural networks, but the diagonal approximation is no good because of the strong posterior correlations in the parameters. And recall, of course, that when he was writing, all networks were small. But I think this view has inspired a lot of work over the past few decades. And we would update it perhaps a little bit, and I'll talk about that in a sec, but let's remind ourselves why we might want to be diagonal, even if we thought that it was a problem for our performance. Well, it's much, much, much cheaper. K here is something like the width of your neural network, assuming fully connected layers. And certainly the gap between something like mean field variational inference and fully modeling the approximate posterior is huge. And even when you start looking at some structured approximations, you get really significant gains, particularly when you're looking at...
Seb, I hate to do this to you, but you're having audio issues again.
Okay, give me 1 second. I'll see if I can fix something.
I guess this is no audio issue, maybe connection issues. Are you back, Seb?
How's this? Is that any better?
Yeah, we can hear you now, but just be aware that maybe if you have connection issues, we will let you know.
Yeah, great, thank you. Here I was just making the point that there are big performance speedups to using mean field variational inference, which might make us want to do this if we could, especially in large networks. And our core idea is that in a more complicated network, you can get away with a less complicated approximating distribution. Now, why might that be? Well, we're updating the story here a little bit to say that the diagonal approximation may well be fine in sufficiently big networks because there's at least one mode of the true posterior which has relatively weak posterior correlations between the parameters. That's a hypothesis. Why might that be true? Well, we have... Did my connection just drop there?
We can see your screen, but are you talking right now?
No, I'm not. Am I connected again?
Yes, you are connected again.
Okay. Sorry about this, folks. We have some empirical reasons to think that increasing the depth of your network might mean
Sorry,
that...
so we actually lost you since the complexity slide. So maybe you want to actually go back a little bit more.
Oh dear. In a nutshell, what our hypothesis is that in a more complicated network, you can get away with a less complicated approximating distribution. The idea for this might be something like what you find with complexity in networks that aren't Bayesian, where the complexity of the connections and the number of parameters lets you express a really complicated predictive function, even though you have all these simple components. And a hypothesis might be that your complicated large network can transform simple weight distributions in a way that lets you approximate a very rich predictive, approximate predictive posterior distribution over the outputs. So we kind of want to update the story a little bit, that the diagonal approximations are maybe fine in deep networks, because in fact there are weak posterior correlations in at least one of the modes of the parameter distribution. Now, why might, like, that's a hypothesis. Is there any reason to think that's true at all? Well, Andrew talked a little bit about analysis using HMC in slightly larger networks. And that's one of the directions that we try to go, where we have here networks that are still small-ish. They have maybe 1,000 parameters each, and a varying number of layers. And what we find is that the additional information cost or Wasserstein distance between the distributions that these HMC approximations reveal and a mean field approximation to those distributions goes down the deeper your network is, keeping the number of parameters roughly constant. So this is maybe making us start to think that in larger networks, as you increase the depth, you're going to be able to get a true posterior that might look roughly right. And we'll notice that here, sort of 2 layers seems to be an important depth, again, which maybe has some connection to the result that Andrew and David had, and can also be explained in some other ways. So we try to analyze things looking at linear networks, where we can do the analysis more simply, and then we'll start to transfer some of these over to piecewise linear networks. In linear networks, depth is just matrix multiplication. And so we can easily decompose one layer into multiple layers, making the network deeper. And even if we're assuming some sort of fully factorized Gaussian distribution over the individual weight distributions, say of B and A matrices, that sort of obviously doesn't entail that the W matrix is a fully factorized distribution over those weights, because the W1 term has within it a product which includes terms that appear in other parts of the full matrix. So what that's saying is, if you're multiplying together in a linear setting a whole bunch of weight matrices, the product matrix can have rich correlations even if the individual matrices don't. And because we're in a linear setting, that's sort of equivalent to saying something about the function, not just the weight distributions. And in the paper, we go into some detail that I'm not going to go into here, which gives some suggestive results in the linear case. One is that 3 or more mean field layers can simulate one full covariance layer, which is to say they can have non-zero correlations between any and all of the product matrix elements. There are some caveats to that result, and potentially a more interpretable one is that a matrix variate Gaussian random variable is a special case of a 3-layer mean field product matrix. So any MVG in the linear setting can be reproduced by 3 mean field ones. And that's interesting just because the matrix variate Gaussian is like a promising structured covariance approximation that people do often make use of. But all of these are for linear networks, and it's reasonable to ask if this has any implications whatsoever for nonlinear ones. And we think the answer to that is yes, at least for piecewise linear activations, which are quite common, like ReLU. And one can maybe extend this to other activations, because what you can do is you can divide the input space into regions within which each of the functions is linear. And for each of those regions, we can define a local product matrix, which gives us some analogous results. And, you know, I'll be the first to say that these results are only kind of suggestive at that point. But we examine some empirical reasons later to think that they might actually be informative. And here's one of them. This is a simulation where we sample weights from a Bayesian neural network, which has been trained on fashion MNIST. And as expected, when you have one weight matrix, which is A, the product matrix is just one weight matrix and is just mean field. And so you've got a diagonal correlations. But as you have product matrices, which are composed of more layers, you start to get these unusual off-diagonal correlations, which have an interesting structure. And so it's clear that this isn't representing some sort of full and free covariance function, but there's some interesting, rich, complicated behavior, and that exists whether you're looking at the linear case or if you're looking at these local product matrices. And I won't spend much time on this because it's a very similar result in some ways to the one Andrew's already described, but we can do some thinking about using the network in between the inputs and the outputs as a universal function approximator. And in this case, what we want to think about is approximating the function that's the inverse CDF of some target distribution. And if we allow ourselves some assumptions about the network, especially if it has at least 3 layers of weight matrices or 2 hidden layers of units, you can start to think about any potential target random variable in your predictive distribution being approximated by your Bayesian neural network. But as Andrew highlighted, like, this is very far from saying that you can discover or learn this distribution. This is just saying that there might be something promising and that this might emerge with depth. And as you get more powerful function approximation with even bigger models, you might be able to get this more closely in reality. So let's quick look at a couple more empirical results, and then we can move to discussion. This is partly repeating the earlier graph based on Hamiltonian Monte Carlo approximations of the posterior, where we're also adding in addition to the ReLU, which was shown before, leaky ReLU with intermediate values and the linear graph, which suggests that, like, there's similar dynamics going on in all of these cases, whether you're looking at linear networks or nonlinear networks, which might give us some reason to think that the results from the linear analysis about how these networks are starting to get good predictive distributions, even with really simple distributions over the weights, might be connected. And then I think there's another angle which is worth looking at, although we need to be careful about what we can infer from it because of all the problems that Andrew discussed about measuring the quality of a posterior approximation in large networks. But if it were true that mean field is a huge and costly approximation, then one might predict that not using a mean field approximation and using some structured approximation would give you a big improvement to results. And it's a little bit hard to assess, and the measures that I'm looking at here of accuracy, NLL, and expected calibration error are only so-so at giving you a sense of whether your posterior is better. But I feel like the takeaway from looking at these sorts of results is that there at least isn't a clear-cut advantage to having a rich posterior approximation of your weights, which might well make you, if you're thinking about production, actually making a trade-off between having a big network that uses mean field or having a smaller network that uses something richer. You might prefer a big, more powerful network. So to wrap up, the diagonal approximation, like, I think Mackay was spot on in 1992 in saying that this was just bad because the posterior approximation had strong correlations. But I think we now need to question that a little bit for larger networks, where there might well be quite weak correlations in at least some modes of the posterior distribution, and we're doing variational inference, so we're only trying to capture one mode anyhow. And that might make us want to look at perhaps other things that are going wrong with our optimization or with our prior construction, rather than throwing mean field variational inference out immediately. Thanks.
Okay, great. I mean, it works well after you fix the network, maybe. Okay, so I guess right now we can go for discussion. So maybe Sebastian, you want to turn off the recording?